good afternoon, everybody. Welcome to another colloquium in the Heidelberg Joint Astronomical Colloquium series. Before we start, I think everybody who's present will have been horrified to hear of the events at one of the tutorials in the university yesterday, and following the request of the president of the university, I'd like to ask everybody to observe a minute's silence for the victims. Thank you. Okay, I think we can break off the minute now and proceed to the colloquium. Thank you, everybody, for that mark of respect. Let's move on. I'm very pleased to welcome today's speaker, Andrea Miglio, who is one of the real leaders in this very rapidly developing field of astroseismology, and is really bringing large impact into knowledge of stellar evolution and way beyond that, in fact, into galaxy evolution. So I ask Andrea's host, Hans Ludwig, to make the formal introduction. Thanks, Hans.
Yeah, hello, also from my side. It is my very pleasure to introduce to you Professor Andrea Miglio from the University of Bologna in Italy. Andrea received his PhD from the University of Liège in 2007. Stayed on for another 3 years at the same place in Liège, but then moved on to the University of Birmingham in the UK, where he stayed for all in all 10 years, working up his way on the career ladder, starting as a lecturer, becoming a senior lecturer, and finally a reader in astroseismology. Last year in February, he became full professor at the Dipartimento di Fisica e Astronomia, sorry to the Italian-speaking ones, so at Bologna University. Perhaps one important thing that happened a couple of years ago was that Andrea succeeded to obtain a ERC grant, an ERC consolidator grant, which takes the keyword, or has the keyword astrochronometry, and this will certainly play a role in his talk today, which is about the assembly history and evolution of the Milky Way as seen through the lens of astroseismic ages. Yeah, also from my side, Andrea, a warm welcome to Heidelberg, and the floor is yours. Please go ahead.
Hello, everyone. I'll start by sharing the screen. Well, first of all, Richard, Hans, thank you so much for the invitation and for the presentation, Hans. I'm truly delighted to have a chance to present to you what's going to be a report on our ongoing efforts to actually try and push the boundaries of the precision and accuracy with which we can infer ages of stars. And I'm also going to talk a little bit about how this improved resolution in age has started to help us understand or reconstruct somehow the temporal sequence of events that shaped our galaxy to what we see today with our instruments. How do we get to these precise ages? Well, we do that by including constraints that come from the detection of global resonant oscillation modes in stars, which is also known as asteroseismology. Now, the road to get to these precise and hopefully accurate ages is long, very long, perhaps longer than expected. But I would say the other important point is that getting precise and accurate ages is necessarily somewhat intertwined with how much we understand, or perhaps don't, about the stellar interiors and stellar physics at large. So I'm going to spend quite a significant fraction of the time of this colloquium talking about models, stellar models, and then eventually show some results about interpreting how these improved ages that can help us understand populations of stars in the Milky Way. Right, so the work we do revolves around stars, and of course the ability to predict properties of stars and of stellar population underpins most of astrophysics. Now, one very strong limiting factor has been, until recently, I would say, that stars, of course, are very opaque. So we have very limited understanding or knowledge or evidence for in the internal constitution of stars or internal properties of stars, with the exception, of course, of the sun, with studies of internal resonant modes in the sun, known as helioseismology, we started already decades ago. But this, for other stars, has actually changed in the last, say, 10 years or so, thanks to the advent of what we usually refer to as the space photometry revolution, meaning that thanks to the availability of space-based telescopes such as COHO, then Kepler and K2, and now TESS, we have finally the ability to detect and measure the frequencies, these resonant frequencies, for, say, tens of thousands of stars across the Milky Way. So opening up also the possibility of studying their properties as they change when you look at different components of the Milky Way. Now, I understand that some time ago, perhaps around a year ago, Connie Arts and also Saskia Hecker, was Heidelberg, by the way, of course, already gave you a presentation about seismology. So I will allow myself perhaps to spend a little bit less time on introducing the basics about seismology, but spend more time on showing you how seismology as a tool can be interesting for astrophysics, and in particular for galactic astrophysics. And of course, if you have any more general questions, I'll be more than happy to discuss a little bit later. Now, the fact that we can, thanks to this new data, measure frequencies very precisely for tens of thousands of stars has several consequences. So the first and foremost, I would say, application of seismology is to perform what we call high precision stellar physics, namely using these frequencies, which have carry quite a significant amount of information about the structure of the stellar interior, to test models of stellar structure and evolution. From the frequencies of, say, acoustic modes, you can relatively easily infer, say, the acoustic travel time across the stellar interior. If you have stars that are, say, sufficiently evolved, like I guess the cartoon is showing here, this is the sketch of the internal structure as we understand it of a giant star, a red giant star, so say an evolved sun, if you like. Then in those evolved stars, what happens is that, given the, I guess, the density distribution inside the star, you may have multiple propagation cavities for these resonant modes. So you may observe modes that propagate as pressure modes in most of the envelope, but then these modes, as they reach the very dense core, they propagate as gravity waves, which are modes whose restoring force is buoyancy. And so this can tell you a great deal about the stratification inside the star. Also quite very local, I would say, features in stars. If you have, say, chemical composition gradients which happen on a relatively small scale, spatial scale, say a scale which is smaller or comparable with the local wavelength of these modes, then this sharp structure variation induces very clear signatures in the oscillation frequency. So we can use those signatures to identify where in the star we have such a sharp structure variation, and then to learn about, say, the sharpness of that spatial structure. So learn about, for instance, the chemical composition gradients, details about the timescale of mixing processes that characterize these gradients. And also, say, if you have a star, typical example, you have a star and you spin it up, then the fact that you break this sort of spherical symmetry and you have these velocity fields induces effects on the frequencies that are observed by, I guess, in the frame of reference of the observer, which can tell you about velocity fields inside the star. And a very, I guess, clear case, and one of the most, I would say, exciting information we got from these evolved stars is information about the rotational profile, especially in the core of the stars, where we have these gravity modes that are propagating in the dense core. So all this data and interpretation have opened up or made accessible, if you like, stellar interiors to our investigations. But this is not all. What you can also do on top of that is to use these constraints also to improve the precision and accuracy with which you can infer stellar properties such as radius, mass, age, and even quite a specific one, but the inclination angle, so the angle between, for instance, the spin axis of a star and the line of sight. And you might say, well, for a given star, this information is not particularly exciting, but then if you can characterize all these properties of a star for a star that hosts an exoplanetary system, this can become quite relevant. And this relevance, I would say, of seismology, which was sort of clear when Kepler data became available and was shown in several papers characterizing planets, has been now, I would say, more widely recognized by the community. And for example, there's going to be a mission called PLATO, which is an ESA medium-class mission, which will fly in 2026 or 2027. Whose primary aim is, of course, to detect planets using the transit technique, but at the same time, PLATO will be able to perform, if you like, asteroseismology on the host star, hence characterize the exoplanetary systems with very high precision. And then again, by using this improved properties of stars, if you think about having such constraints on tens of thousands of stars across the galactic disk and part of the halo, then you can think about using these improved ages, that's really the main constraint here, and use stars as fossils to reconstruct somehow the assembly history and chemodynamical history of the Milky Way. And this is what I'm going to be mostly talking about. And specifically, I'm going to use as traces of age or proxy of age stars that are quite evolved. So these red giant stars, which are actually very good proxy for the to probe the evolution in time of stellar population at large distances, and also they span quite a wide age range. So the idea, which is of course quite simple, is to couple constraints that we have from different sources, from Gaia, so astrometry, parallaxes, and proper motions, with information coming from spectroscopy on velocities, but of course primarily on the surface chemical composition of stars, with constraints that come from astroseismology, which can help us infer ages of stars. And this is a typical power spectrum, so power spectral density of a pulsating giant, where you have frequencies here on the x-axis, which are in microhertz. And when you see this, I guess, regions or lines of power excess, those correspond to resonant oscillation frequencies of the star. So you see we have quite a number of these frequencies, and I'll talk about these in a minute. And this is a sort of line of work that I've, together with a few collaborators, started to push already, I would say, maybe 10 years ago, 2008 or so, when we had the very first data from GOHO. And then we realized the potential of this. And of course, in the meanwhile, the field has matured, more data have become available. And the other thing that makes or made a significant change, as Hans was mentioning, is also that it was possible, thanks to the ERC, to set up a team, which is quite interdisciplinary in nature, where we work together as a team, of course, having people, I don't know, like me, who are expert perhaps in stellar structure and seismology, but also people who main expertise is spectroscopy, others who are knowledgeable about models of chemodynamical evolution of the galaxy, and of course also including input from very precious collaborators. So we're trying to work together in this and tackle this rather complicated problem from different angles. And so also the work that I'm going to show, or the results that I'm going to show today, are 90% from my collaborators. So going back to the project itself, as I mentioned, we're trying really to get to to test ways of getting the most precise and accurate ages. And the way we do that is following different approaches when it comes to inferring these properties. So typically what we have is a series of models, of stellar models, for which we can predict oscillation frequencies. And then we have ways, of course, of comparing these frequencies with observations, but that can be done in quite different ways. And I'll tell you a little bit about that in a minute. And then, of course, we also use in I would say, controlled environments, if you like, or well-constrained systems, such as clusters. We use the asteroseismic constraints to try and improve or at least calibrate some of the parameters in the models, because these are the very same models, stellar evolution models, that are used to infer ages. So we're trying also to improve those. And also a key point in all this project is to try and validate inferences about masses and radii done using seismology on single stars against independent estimates. And this is also difficult given the precision we are aiming for. And so eventually, when we get ages we trust, then we try to use those to understand features of population or the evolution or the assembly history of some components of the Milky Way. And in terms of different approaches, as I was introducing a little bit earlier on, a typical data that we have for seismology look like this plot here, where you have the power spectral density as a function of frequency, and this is obtained, I would say, simply by taking observations, photometric observations, photometric time series of flux as a function of time. In this case, for about 4 years, looking at a star in the Kepler fields, and then by looking at the frequency contact of that time series with the Fourier transform. And one can start characterizing these oscillations in red giants by two parameters, which we call average seismic parameters, which are this nu max, which corresponds to the frequency at maximum oscillation power of a smooth spectrum. And then this delta nu here, which is a typical spacing which tells us about the sound travel time, which is also related to the average mean density of the star. These are two parameters that one can measure from the spectra, and they are related to mass combinations, I would say, of mass and radius of the star. So by having these two parameters and information from spectroscopy, one can infer radii and masses. This is also the delta nu and nu max in a nutshell. But of course, especially for Kepler data, the oscillation spectra contain so much more information than these two parameters. And you can clearly see it in, well, it's the same plot, of course, but here in the bottom panel, I'm really highlighting the fact that you have many modes, tens of oscillation modes that you can measure very precisely given the duration of the time series. So what we're trying to do now is to include individual mode frequencies in the modeling, since these modes contain quite a lot more information. And to give you an example, of course, I don't want you to look at the details of the table. We are using a code or developing a code where you use just this average seismic parameters, but trying to be quite careful of how you define these averages. These are all small effects, but again, if one aims at an age precision of 15, 10%, then every little detail counts really. But also crucially, we've started to explore systematic effects that can indeed have an important effect on the ages. And again, in this table, if you're interested, I would say the paper or the table here, we went through this sort of painful exercise of looking at various components in terms of systematic effects. What if not only seismology is a bias, say, in these stellar models, but also what if the estimates of chemical composition, say, of metallicity from spectroscopy are offset by 0.1 dex? What happens to the ages? And there is certainly an effect. So we've used this test to then extract the trends that we find to be robust against these systematic effects. This is one way of modeling. Then what we're trying to do now, as I mentioned, is to take a step further and use individual mode frequencies. And I'll come back to this paper towards the end of the colloquium. But here, what we're trying to do is understand a little bit better the information content that is carried by these different frequencies, and try to devise also combination of frequencies or seismic diagnostics that are robust against model uncertainties. And so we try then to model not only average parameters, but individual modes. As you can see here, it's a I guess just a plot showing the data in black, and then the models that we have for modes of different angular degree. This is what L stands for, how they compare with the observations. So now I'll get to the part where I'll just give you a few examples about the work that we're doing. First of all, in terms of testing seismic determination of mass and radius against independent constraints, what we're doing there is make use of anything that is available, but for which we have, I would say, precision on the mass or the radius, which can be comparable with the very high precision you get from seismology. And we're lucky enough that there are certainly a few clusters that have been observed, say by Kepler, for instance, or K2, in which we can detect oscillation. I mean, in giants in those clusters. And this plot here is just a very simple plot showing you the correlation that we know exists between the mass of a red giant branch star, so one of these evolved stars after the main sequence, and its age. And it's really this correlation that we're using, which enables us to get precise ages with the giants, because from seismology, you cannot determine directly an age, of course, there's no way to do that, but we can infer the mass. And the mass is a very, very good proxy for the age in that evolutionary phase. So here we have a few clusters that we've used to test masses and indirectly ages and radii and distances, starting from NGC 6811, it's a high-dislike cluster, so a bigger year-old cluster, up until N4, which is the only globular cluster in which we have detections of solar-like oscillations. Then we're also using Gaia and eclipsing partners, of course. Just to show you some examples, Gaia has been incredibly useful for us in this context, of course, on top of being useful for 1,000 other things. But the point here is that, of course, with Gaia, you can measure parallaxes. With seismology, this might be not super intuitive at the beginning, but you can also indirectly infer parallaxes. And the way you do it is the following. So for stars with seismic constraints, you can infer radii very precisely to a couple of %. Then, of course, if you have a radius, a photospheric radius, then you can couple that with an effective temperature via Stefan Boltzmann law and get a luminosity, a true luminosity of a star. And then by comparing that with the apparent luminosity, you can infer a distance, hence a parallax. So this is what this plot is comparing here, is the what's the asteroseismic parallax, if you allow me to use that word, which is on the x-axis, against the parallax as measured by Gaia for the same stars. And it was really a pleasure to see that once, I guess, a little bit of modeling is done as well. We're not just using some off-the-shelf scaling relations, but doing just a little bit of modeling, then you get an extremely, it's not just a tight correlation. I mean, you see that actually we have a very good agreement between the two determinations. Of course, what we also noticed is that this is Gaia data release 2 data. There is an offset between the seismic and the Gaia parallax, and a large fraction of that offset is probably related to the Gaia 0-point offset issue. So in here, what I was showing is the comparison for stars in the giant branches, but in 2 different evolutionary phases, where again the model predictions are actually quite relevant to correct for the parallaxes instead of using some simple relations. Then, of course, if the interesting part of the paper is to get to the details, which I will not have time to describe here. But then also in that paper, there was quite a lot of work in trying to get a handle on the systematic effects, especially from the seismology side. What if we use the different grids of stellar models? What if we used different effective temperature scale from seismology, trying to understand the role of all these biases. And the reason why we do care a lot about the radius from seismology is that the way we infer radius and mass using these constraints leads necessarily to a very tight correlation between mass and radius. Meaning that, of course, if we do see a strong bias in the radius using Gaia data, then there's a very high probability that we're also getting the mass biased or biased estimate of the mass, which means then a significant effect on the age. So this is why, even though Gaia is not delivering masses that we can compare to, already having radii independently determined is helping quite a lot in checking what we're doing with seismology. And of course, Sanya is now almost ready to submit a paper where she has extended the sample. So these were what I was showing earlier on with stars from the Kepler field. Now we have applied the same method to different fields observed by K2 and TESS, and using Gaia EDR3, so more recent data. Then another example here is in this case on a cluster, NGC 6819. It doesn't really matter which cluster I pick, but here the plot now we use to show this comparison has, in this case, a distance modulus on the y-axis and the mass on the x-axis. And you see here this band, this shaded band illustrates the constraints we have, the 1 sigma interval of the distance and mass as determined using eclipsing binaries at the turn of this cluster. And then all these red and blue dots here represent a measurement or an inference on the distance and the mass of a few giants observed by Kepler. And you see that the agreement for most stars is actually quite encouraging. Now, what you also see, which I would say potentially even more interesting, is that there are stars like this star here and these yellow dots there that are located at the distance of the cluster, if I may say so, but have a mass which is significantly different from the mass that is expected for red giant branch star. So the red giant branch phase is quite short-lived. So you expect most of the stars or all the stars on that phase to have basically the same mass. But there are some that are significantly off. And what we think is happening here is that what we're seeing is an evidence for stars that underwent either a significant episode of mass loss, like this star here, or stars that experienced a mass transfer event or are, say, products of mergers. So even this was not the intended, I would say, scope of this test, we could find clear evidence for that. And I'll come back to this overmassive stars or products of mass transfer a little bit later on. And just another, and the final example on tests that we're running. This is work done by Andreas Jørgensen, where we've used a few eclipsing binaries for which we have precise measurements of radii and masses independent from seismology, and then use this method where we fit individual mode frequencies and compared the seismic determination of radius and mass with the independent one. And what we've done there was primarily to play with one of the systematic uncertainties we have in the models, which we often refer to as the surface effects, which originates from our, I would say, ignorance about the stratification of the outer layers of the star and also non-adiabatic effects in the oscillation. So we use a parameterized way of taking those into account and use the eclipsing binaries to somewhat calibrate some of the parameters, so at least choose which parameterization gives the most accurate result compared to eclipsing binaries. And in general, well, you can see this is a plot showing the difference in radius normalized by the uncertainty or in mass between the seismic and the radius or mass determined via the fit of the EB light curves and radial velocities. You see that in most cases we are around, I would say, 1 sigma offset or so, which is again quite encouraging. There is one case where the offset is actually quite large, and it turns out having more data also from the eclipsing binary side of things is helping quite a lot, because again the challenge here is that from seismology, just because the frequencies we measure are so precise, we end up with masses that are very, very precise to say 1%. And then it's not easy to find targets for which you have measurements of mass that are with an uncertainty that is comparable to that. So that's really one of the challenges we're facing. Okay, so that's, I would say, enough about examples of how we're comparing with independent estimations of masses and radii. Now I'm just going to switch to the some efforts in testing models of stellar evolution, or at least calibrating model parameters. Right, so the situation we have is I guess illustrated by this plot. This is a Hertzsprung-Russell diagram, which is entirely made of data. which, I mean, from someone who's used to computing models, this would look like a synthetic population. But it's actually data where the effective temperature here comes from spectroscopy. The luminosity has been evaluated by using or incorporating, of course, Gaia's parallaxes, and the mass here, so which is the mass scale is you can see that by looking at the color here on the plot. That comes from estimating masses using seismology. So, I mean, if you are a stellar evolution enthusiast, you probably appreciate already what you could do with such a plot. Looking at overdensities of stars, say in this area here, you can characterize what we call the red giant branch bump. You have this very even clearer overdensity of stars, which is the red clump, and that's this region in the HR diagram where low mass stars burn helium in their cores. So low mass stars will go through the helium flash. And then when you move to higher masses, you have first in the core helium burning phase, first you have a sort of decrease in luminosity, which corresponds to the minimum mass of the helium core. Non-degenerate helium core then can burn helium. And then as the mass increases, you have an increase in luminosity. So you're really seeing, if you like, stellar evolution with this data. And so what we're doing to some extent, it's quite simple. It's just somewhat revisiting questions that have been around for decades, that are in books of stellar evolution, just being able to tackle some of these questions thanks to this data. And first of all, well, with seismology, one can easily distinguish between stars that are in the core helium burning phase as opposed to stars that are ascending the giant branch. So if we focus on the red clump, so where low mass stars burn helium in the core, then one can look at some patterns of frequencies or periods, which we call here delta pi, which are very sensitive indicators of the properties of the core, and compare those, this in two clusters, so again, using this sort of controlled environment, and compare those with various ways of modeling the evolution or the mixing at the boundary of a convective core that is there in models that are burning helium. And in the models, this is a very delicate situation because you have a core which is convective, so basically fully mixed, that in this evolutionary phase increases in mass. So in principle, it would generate a near discontinuity in the chemical composition profile. This is numerically and also I would say theoretically quite hard to implement in stellar evolution code. So we're taking an approach which is very simplistic, so trying just to parameterize this mixing. And so you can already, by comparing different recipes or prescriptions for that mixing, exclude some of the models. And so at least, if not understand what is the physics behind mixing in such a complicated situation, at least we can somehow parameterize our ignorance with this data. And this might seem like a little detail for those who care about stellar interiors, but in the end, I mean, depending on the mixing scheme that you use, then this will have a significant impact on the morphology of the tracks in a color magnitude diagram. And these are the same tracks that are then used to build synthetic populations or integrated spectra. So this sort of details about stellar evolution that we can now probe can have some quite some interesting implications and wider implications. Still about mixing, and this is an example of in this case, truly a color magnitude diagram based on targets that are observed by TESS, so looking at relatively nearby stars. And here, what we can see is an additional overdensity of stars here, so above the clump. And this is known as the AGB bump, that previously was basically known or seen only in clusters, but we can see that also in field stars. And the luminosity at which this AGB bump occurs is determined in the models by the luminosity at which the helium burning shell is ignited, which depends again on how big the carbon-oxygen core is at the end of core helium burning. So by combining this information with seismology, then again, we have a chance of calibrating at least the models, eventually, hopefully, testing some more elaborate theoretical prescriptions. And then another last example about the clump. Again, just looking at books, one can sort of understand that the clump, the luminosity of the clump, which for low mass stars is generally thought to be quite uniform, because again, all these stars go through a flash, and so they have a similar mass of the helium core. In reality, there are sort of second order effects, which we can now measure. And so the luminosity, even in the clump, will depend on the mass of the star, on the chemical, I would say on the metallicity, as we call it, but also on the helium abundance. And the helium abundance, at least in the photosphere, is not something that you can infer using a spectroscopy for these very cool stars. And so this has been one of the major, I would say, free parameters in models that hardly is actually kept as a free parameter in, in isochrones, etc. Otherwise, you have no constraints. But the initial helium certainly has a very strong effect on the ages, for instance, of stars. So what we're doing here is quite simple. This is work which is being carried out by Emma Willett, who was a PhD student in the group. And what we're doing is the following. So have a look at this part of the plot here. So the black histogram is just a luminosity distribution, where luminosity is computed using Gaia parallaxes for stars with a mass around, in this case, 1.2 solar masses, and with a low metallicity. This is FU over H, the beam centered around minus 0.4. So the black histogram are the data, and then you have the colored histograms are the distribution of luminosity from synthetic populations, where what we do is to change the initial helium mass fraction. So we start from 25%, I guess the blue histogram here, up to 34%, which is the red one. And what you can see, literally see in this plot, is that when you consider stars of increasing metallicity, FU over H, you see that the stars increase their helium mass fraction. So you move this black histogram closer to a model with, say, 28% of helium in mass, up to around 32%. This is, of course, expected. This is sort of chemical evolution somehow of the galaxy itself. But we have now a chance of measuring that evolution. And this is important because then you can somehow use that chemical enrichment relation in the model, so have a more precise age. On the other hand, it's also interesting, and this is what Fiorenzo explored a couple of years ago, to then compare this chemical evolution that we see in the Milky Way with predictions from chemical evolution models of galaxies. Right, so getting to the bump, just some words about that. So the bump in, I guess, 30 seconds is a feature in the color magnitude diagrams, which originates, and that was understood already in, I think, in 1967 by Thomas, by the fact that when the hydrogen burning shell in these models moves close to the chemical composition gradient that is left by the convective envelope as it goes deeper and deeper into the star, then the evolutionary tracks basically spends, or the star in the end spends more time in that region as the shell adjusts its energy output to this changed chemical composition. And okay, this has been known and seen in clusters for decades. But now we have a chance of seeing the properties, or determining the properties of this feature in a wide population. And the interesting part is that the luminosity of this bump depends strongly on how deep the convective envelope is. So if we have uncertainties about additional mixing at the boundary of the envelope, this is going to affect the position of the bump. And this is what Seismic did, looking at the position of the bump, in this case, nu max, but it is a proxy basic of luminosity. And if we look at this panel here, what we have is the position of this bump for stars of around 1 solar mass, and how the position changes when we consider stars of different metallicity, from metal poor to metal rich. And then we compared with models, which are these colored lines here. So the yellow line here is for a model where we don't add any additional mixing beyond the Schwarzschild boundary of the convective envelope. And then we have an increasing efficiency of this mixing, moving from purple to red. And what you can see is, well, first of all, that we do need in these models additional mixing, as actually we need for the sun, and that we know already. But what is also quite intriguing, and I think potentially the most interesting result here, is that what we see is that we need, I would say, that this mixing is more efficient when we look at metal poor stars than metal rich stars. And this could be just giving us a hint about the actual mechanism behind, because of course, the efficiency of a mixing, be it say, overshooting, so related to the penetration of convective plumes beyond the solar shield boundary, the efficiency of this mixing might depend on the condition of the environment, so the density profile or the density itself, or the stiffness of that boundary. And considering stars or environments that are metal poor, in general, they have a smaller stiffness of that boundary compared to metal rich. So this is just a hint that we'd like to explore a little bit more, especially checking against predictions of more realistic and hydrodynamical simulation to see if what we're really seeing is an effect of convective overshoot. Right, and then probably the last slide on testing stellar physics. This is about the occurrence of mass loss. We know is a phenomenon occurring in low mass stars on the red giant branch. And here the idea is to look at a population which is quite simple, so the alpha-rich population, and consider stars on the AGB, so this bunch of stars here, look at their mass distribution, which is here, and compare it to the mass distribution of stars in the red cloud, with the idea that mass loss occurs basically up here, where the star is near the tip. So the radius is basically 1 AU, and the surface gravity is so low that it's quite easy or energetically to lose mass. And by comparing these distributions, then we can actually infer or measure this integrated mass loss, which again is an extra constraint we can use in the models to improve the ages. And another point here about some outliers. There's clearly a few percent, say 5% on the AGB, and maybe 10% or more in the core helium burning phase of stars that are overmassive, stars that are either very young, but with a chemical composition that we don't expect them to be young, or most likely stars that have actually undergone significant mass accretion or products of mergers. And so there's a lot of work that's been done by a student, Walter van Rossum, and together with Rob Izzard at Surrey, to try and make predictions based on binary population synthesis to see if we can understand or spot or find a signature, a seismic signature of these overmassive stars also in the field, right? Because in a cluster, we can sort of easily spot them. In a simple population, perhaps, but then in the field, that's very difficult. And that can have consequences also when it comes to understanding or characterizing secular transport process in the galaxy. So the timescale of those processes could be, the inference can be completely wrong if we have ages that are off because of these products. Right, so that takes me to the final part of the presentation. As I promised at the beginning, I was going to show you some examples of how we can start to use ages. And this is some plots from a paper we published last year, myself, Christina Chiappini, Ted Macrath, and a few collaborators. These are all stars in the Kepler field. So in terms of galactic structure, we are looking at stars that are, well, most of them are at the same galactocentric radius as the sun, looking slightly above the plane. And so, while one can spend hours trying to interpret the correlations between age and Fe over H, for instance, or just looking at the how the distributions of Fe over H become wider as one looks at older ages and associating these features to, again, transport processes, radial migrations, etc. I'm just going to focus on a couple of things here. First one is the, well, I guess, strong correlation again between alpha over Fe and age, but especially on the fact that once you get to an alpha, say, roughly speaking, above 0.1, and alpha over E, so over Fe above 0.1, then we are looking really at a population that looks like a cluster, like almost a mono-age population. And this is what we're showing here. So looking at these 400 alpha-rich stars with robust ages, so we have a mean age which is about 11 gigayears, but that, I mean, systematic effects can move that number by at least a gigayear. So one has to be a little bit careful. But what we find to be very robust is the intrinsic spread of the population, of the age of this population, which is of course not the width of these probability distribution functions, which are dominated by the uncertainties. But if you try to apply a statistical model, then you end up with a population which has an intrinsic spread of the order of less than a gigayear. So this is probably one of the first time where what people thought, of course, that the I alpha population would be very old. We can actually measure that for a few hundred stars. That's quite exciting. And then you can take it a little bit further and look at age velocity dispersion relations, where, for instance, here we find we're looking at the vertical velocity dispersion, and finds that the model where we have basically a different age velocity dispersion relation for the low alpha and the high alpha disk is the preferred model. Again, this suggests that these two populations really had a different dynamical history and a different formation history as well. And these are the population that one may call thin and thick disk, and I'm not going to get into how one defines chemically or I would say kinematically these disks. But anyway, the old population and the young population, if you like. And then the final example here is a result which was published last year by Josefina, a paper led by Josefina Montalban. And there is, as I was showing earlier on, where we applied this improved technique to infer ages. And there we were lucky enough to find among the Kepler metal poor stars a handful at least of stars that are most likely to be stars accreted from another galaxy, which was called Gaia Enceladus. So what we tried there is to get robust differential ages of metal poor stars and comparing the ages of this accreted population with the ages of what you might call in situ stars. And this is hard because we're looking at stars that are 10 giga-years old. So you see that, at 10% is already a giga-year. So it's tough, but we think we have found ages that, at least in a differential sense, are quite robust. So the main finding there was to see that the ages of the in situ populations, the distribution of ages, this red line here, shows us that there are certainly a significant fraction of the in situ stars that are older than the accreted population, which is this green distribution here. Meaning also that there's this sort of gives evidence that what one may call the thick disk or the in situ population was already there before that merger occurred. So the merger was probably important for many reasons, but was not most likely wasn't the what originated the thick disk. Right. So I'm getting to the first summary here. So one takeaway message would probably be that the inference that we're making on stellar properties with seismology is rather complicated question if one wants to discuss precision and accuracy. It is true in any case that seismic inferences to the level of a few percent are model dependent. There's no way around that. Details about the models, they do have significant effects on the oscillation frequency. So depending if you're a half full or half empty glass person, you can see it as a negative thing. So that will limit certainly the accuracy in the determination of the age. But on the other hand, if you have very well controlled samples of stars or clusters, then you can really improve models because the frequencies are very sensitive to details there. So that's why, again, developing stellar models is necessarily very much intertwined to determining properties of stars. And then I'll just give you a few examples on how we're starting to couple Gaia, spectroscopy, and seismology to constrain some of the models, and eventually also to apply, to infer ages and use these ages to understand or reveal at a higher, I would say, temporal resolution, the history of the Milky Way. In terms of plans, a lot of plans as usual. We're going to extend this detailed modeling to thousands of stars now, and also take another step, which is to compare the age distributions we have with realistic, or anyway, more elaborate chemodynamical simulations of the Milky Way, trying to take into account selection biases and try to quantify various contributors to the what actually shapes the Milky Way. Now, just a couple of final slides here in terms of data. We have a lot of data at this moment. There's Kepler, there's more fields. Coho data are being reanalyzed. K2 has observed different fields, but it's not Kepler in terms of resolution in frequency, so it's not quite the same constraints. There's TESS, which is a local sample, but has exquisite data from Gaia. And then if you have a little bit of patience, 2026, PLATO will be launched. And then PLATO has the ability of being a real complement to Gaia to some extent, because you will be able to detect oscillations of stars in principle up to 50% of the sky. And that's, it will take a few years. But what we've also done with a few colleagues is to try and take a step back from this sort of sumptuous feast and started to think if new data and more data are needed to push even further the limits in terms of stellar modeling. And the reality is that, I mean, the very stringent constraints that we could put on the models are only possible when you have a, I would say, controlled environment, meaning clusters. And so that's why, together with Leo Girardi and a few colleagues, we put forward an idea in reply to the ESA Voyage 2050 call of a concept for a mission. And I hope this is not going to sound too much like a commercial, but we're thinking about, maybe 20 years time from now. But the fact that I would say Corot and Kepler, they clearly demonstrated the potential of seismology in clusters and getting really to the details of models. But then TESS and PLATO, they are missions that are not optimized for stellar science. They are missions that are going to look for planets. And this means they're looking at the wide field, bright targets, very large pixel sizes. And so to try and overcome these limitations, we would like to get Kepler-like, so extremely precise observations, but in crowded stellar fields. And this is what we think would enable more breakthroughs in stellar and galactic science. And that's why we've devised, this mission. I'm not going to spend or take too much of your time on that, but we have as objectives on the one hand, high precision stellar astrophysics, especially in the meta-poor regime. So looking at basically high Z stars, if you like. So having very detailed constraints about transport of chemical elements and angular momentum, mass loss, mergers, etc. But then also trying to answer some open question on globular clusters. So we will be targeting a few globular clusters, so multiple populations, or a distribution of angular momentum based on the detection or the determination of speed axis inclination. And then we also have a component on, galactic structure and evolution, looking at the bulge, which is a very dense field that cannot be done without emissions, trying to, reveal the star formation history there, and also look at a couple of nearby dwarf galaxies. So we put in that proposal, we got encouraging feedback, I would say, from the Voyage 2050 senior committee. So now we're moving to the next step, which is to submit a proposal with a deadline, which is in 3 weeks' time. It's just the first proposal where we just want to basically, again, make the case for the mission, and then if it looks reasonable to ESA, then we'll be invited for a phase 2, where we have to be much more detailed. But of course, the point for showing you this is also that we would very much value your help, support, criticism, feedback to improve this idea and see how to go forward from this. The consortium is completely open. We are trying to set up now a scientific and payload consortium. But if you're interested or you care about these scientific goals, you're very, very welcome to get in touch. And I will stop here and thank you so much for your attention.
Thank you very much, Andrea, for this insightful overview into the current developments increasing the precision. And I'll invite questions from the floor. So please use the chat or put your hand up. We have one question already from Andreas Just.
Yes, Andrea, very interesting talk and overview. It also looks like a big improvement in the precision or accuracy of the astroseismic models. But I still have a question to the fundamentals. Yeah, so I remember from all these early determinations, or let's say in the last years, that one of the critical quantities is the sound speed profile of the stars, which are not consistent with the stellar evolution models. With your new approach of modeling all the frequencies, do you get a significant improvement in that direction? That it's now more consistent, or what is the status?
So if I'm not mistaken, I guess the inconsistency that is found, and it's very clear, is in terms of the sound profile of the sun, where using the sort of updated abundances or photospheric abundances has shown that the solar model, when you compare it to the inferred sound speed profile from his helioseismology, shows very strong inconsistencies or disagreement. So this is the case for the sun. And the solution to that problem is not entirely clear yet. Some people in the field tend towards a solution which might come from yet another time the underestimation of opacities or radiative opacities. So this is a clear problem for the whole community. And we would be too naive to think that the model of the sun is wrong and the rest is necessarily correct. For giants, I think what helps quite a bit is that we have a few stars, or say eclipsing binaries or clusters, against which we can at least compare the inferences, or against independent determinations, which is not always the case for main sequence stars. But of course, it's also to be seen whether the differences we have in the solar model, which are very strong and tells us that the details of the structure they're not known accurately enough, whether they have an impact on the global parameters we're trying to determine here. So I would say in the sun, we are a few orders of magnitudes above in terms of precision at which we're testing models. And for other stars, and especially with giants, what we're relying on now is comparisons against independent determination of masses of the order of a few percent. So in this, I would say, area of work, I've underlined mostly the aspects that have a direct impact on the mass and the age of a giant. There are things we completely don't understand in giants, the internal rotational profile. That is completely wrong in the models. But that ignorance, I would say, doesn't have, at least as far as we understand, a very clear and direct impact on the estimates of masses and ages.
Okay, thank you. I understand.
Okay, Hans?
Andrea, I was a bit wondering about your comments on PLATO and TESS, since both are missions that of basically small telescopes. You mentioned it in one of your slides yourself that concerning galactic structure, they are not able to provide information about populations a bit further away, so little information about the Milky Way as a whole. I mean, you were putting forward Haydn. I guess it was a consequence of this. How large a telescope do you foresee for Haydn, the aperture, and what's your general take on PLATO and TESS?
Yeah, so I guess the main limitations of PLATO and TESS is not the telescope size, but just the fact that they're looking at, well, a wide field, and they have very large pixel size because they're looking at nearby stars and bright stars primarily. Yeah. So with TESS, for instance, there's about maybe 100,000 giants which we can get a detection, but we're really looking at stars that are within 1.5 kiloparsec. So you're not really able to probe very far. For PLATO, in principle, we can go further. In some fields, it will be possible. Maybe I can go back to the slide here. The limitation there is going to be that even PLATO is not going to be able to infer, say, or anyway, to measure. To measure oscillation frequencies very precisely for dense fields. So the bulge is going to be extremely difficult for PLATO to have information there. And also really the very strong limitation is that with PLATO or TESS, we're not going to be able to detect oscillations in clusters, globular clusters. It's just the fact that the pixel size on the sky is so large that you will get contamination from many sources. So that will prevent very strong tests of stellar models, especially in the metal poor environment, which were possible to some extent with Kepler. So results on clusters in Kepler are very promising, but they're not really probing the very old clusters. So that's some other limitation. So it's more on the density of the field, that if you're looking at dense fields, TESS and PLATO cannot deliver high precision seismology there.
The aperture of the Haydn instrument, is there already an idea?
Yeah, so the idea is that a telescope, which in the end would look like Kepler, so a 90 centimeter diameter would be enough to detect oscillations, say, in globular clusters down, possibly down at the turn of the globular cluster. So it doesn't need a particularly large mirror, but it's just the way it is designed and the ability of, I guess, the spatial resolution somehow to avoid contamination in dense fields. That is not, unfortunately, something that PLATO can do.
Thank you.
one last question, I think, from Ralph.
Thanks, Andrea, for this very interesting talk. I have a question that I don't know, you know the answer, but which I think is very puzzling. And since you mentioned globular clusters and old metal poor stars, it seems that there is a huge problem with the existing stellar evolutionary tracks in the low mass, let's say subsolar mass range and low metallicity regime, in the sense that when we take stellar evolutionary tracks and look at the photometric output, it does not fit generally globular clusters. Unless you introduce some fudge factors that correct for the photometric fluxes and bring it up so that the color magnitude diagrams of the synthetic clusters agree again with the observed clusters. So I was wondering whether you have any idea where this discrepancy comes from, and whether you think this new mission or existing missions have or can contribute to solving this puzzle.
So first, I'm not an expert there. There's been a lot of discussions also within, say, within PLATO, for instance. PLATO is going to target some of the, say, the late type giants looking for planets in the habitable zone. And there's clearly lots of discrepancies in models potentially related to, atmospheres or convection there or activity. The mission that we're looking at, so in terms of, I would say, of seismology, unfortunately, looking at late type stars, the amplitudes of these oscillations become so small that they're not going to be detectable with any of the missions that are planned so far. So it is certainly an extremely interesting line of work, but I don't have any answer basically to that question of whether these observations or I guess a photometric follow-up in terms of time series or looking at variability, in most cases, going to help us necessarily. That I don't know. Confess my ignorance.
Okay, thanks.
Okay, thank you very much. We'll have opportunity for more discussion in the extended Zoom session after the formal colloquium is over. Before thanking Andrea again, I'd like to make an announcement about next week's colloquium. So I'll just put share the screen to do that. And that colloquium will be considering some of the most spectacular observations of the early stages of planet formation by Miriam Benesty from Planetary Sciences in Grenoble. So that's something to look forward to next week. So let's open up our screens and open up our microphones as well, if you'd like to give Andrea a really great send-off for such an informative and interesting talk. Thank you, Andrea.